Okay, good morning, everyone. Welcome to APNIC eLearning web class. Today is Wednesday, the 17th of June in 2015. It's already actually afternoon, 1 p.m. in the afternoon in Brisbane in Australia, where I'm broadcasting this class. Now, this is the second session that we are doing for the day, and it will run for 1 hour. The topic is about BGP. Earlier in the morning, if you have attended that, that was about routing. So you probably already have some good overview of routing, and now we will go on to discuss about BGP. Now, before I go on to the details of what we're going to cover for the next 1 hour, just a brief overview of myself. My name is Cheryl Hermoso. I work for EPNIC. I am part of the training team, and as in our team, we do conduct trainings, workshops, either face-to-face or online to the members of the internet community. So with that, we do different topics that are all related to what we do, our core business at APNIC. So we do network security, DNS and DNSSEC, IPv6, routing and BGP, and also internet resource management. Now for this class particularly, I will be asking you to fill in a survey. So I'll write down the link towards the end of the session. Please try and fill it in. It's not very long, and it will be very helpful for us going forwards, especially on how we deliver these kinds of topics. Okay, so what are we going to cover? This is BGP, right? So we will look at the details of BGP. What is it? What is it for? What are the features of BGP? In more details, we'll look at, of course, BGP is a path vector routing protocol. So let's try and understand that a little bit, how that routing protocol works. We will look at some of the terminologies that we use largely with connections of different networks or different ASs. We'll look at peering and transit and what's the difference between them. We will look at the general operations of BGP. Very briefly, we will also try and discuss about BGP attributes. We have a different session that discusses that in more detail. So here we just want to introduce BGP attributes because it has a lot to do with how you can control traffic, either incoming or outgoing, going outside of your network, right? And then some examples towards the end on how you can add or configure BGP on your, I think the example that we have here is Cisco router, and how you can announce a prefix or an IP address block that is assigned to you. Okay, let's go on to the details of that. Now, for this session, it's a technical topic. Obviously, it's aimed at people who wish to advance their knowledge of networking. Some of you may have already done a bit of configurations yourselves, perhaps. Maybe you're maintaining your IP networks. Maybe some of you just have a general interest in the topic. So we'll try to cater for both of these. But generally, it's really very technical topic. So some background of internet protocols, TCP/IP would be good coming into this class. Now, our discussion requires that you have a fair amount of those kinds of routing protocols as well. And as I've said, if you have been through the first session for this morning, then you're good to go. So what is routing? Okay, or what is BGP? So what is routing first? Routing, as you know, is a process of forwarding packets, right? You have different networks. You want to pass one data basically from one network to another, from one source to the destination, and it uses L3 devices. Either you have a router, or in the previous years, in the earlier days, they call it as a gateway. So you need that L3 device. BGP is a routing protocol. It is defined in RFC 4271. It's a routing protocol that can be used to do routing between networks. So if you look at the RFC, and I'm just like letting some people in, that's why I get distracted quite a bit. In here, when you look at the RFC 4271, it contains the BGP4 specifications. It says there that BGP is an inter-autonomous system routing protocol. So you must understand what's an autonomous system, okay, to be able to understand BGP as a whole. the primary function of BGP speaking systems, you'll have routers, we call them as BGP speakers. Their primary function is to exchange routing reachability information. We call it as NLRI, network reachability information with other BGP systems. This network reachability information includes things like the list of autonomous systems that are reachable from them, okay, and the information about how to get there, how to traverse there, okay. This information will be sufficient so that you can construct a graph of ACE connectivity for this reachability, so that routing loops can be prevented, or in that case can be pruned at the AS level. And then you can also do some policy decisions, you can enforce them. So basically that definition, you can find that in the BGP4 specifications in RFC 4271. Okay, so if you look at that more closely, there are a few things that you have to understand, of course. Autonomous systems, so it says that it's a list of autonomous systems. Another one is routing loops. What is it? And lastly, policy decisions. Okay, those are the things that impact BGP. So we will look at them in more detail as we go on, so you'll have a deeper understanding of what they do. So basically, to simplify this, the definition of BGP, essentially, it's a routing protocol. It's one of a few other routing protocols that are available. It defines how to route your information, your packets going in and out or around your network. Whereas the routing is concerned with finding the best path of a destination, obviously BGP has the same goal. There are many possible routes going to a destination. Okay, each of them have varied metrics or varied things like latency, distance, bandwidth. Perhaps there are other different metrics out there. There are two general types of routing protocols, internal or external. For internal, we call that as IGP, Interior Gateway Protocol. It's used to transfer information within the network. Some examples are RIP, EIGRP, OSPF, ISIS, and so on. Now, the other type is external or exterior gateway protocol, or EGP. Now, the first and only actively used EGP now is BGP, Border Gateway Protocol. Okay, so a simplified definition of BGP would probably be, it's a protocol that's used to exchange information between different networks. Okay, so you can consider it as one of the most useful protocols that runs the internet. Some people would even say it's the internet routing protocol for the internet. Okay, it's very simplified, but it kind of gets the essence. Now, the standard specification of BGP is in RFC, so you can see there, RFC 4271. Okay, there are two things that you can look at as well, RFC 4276, which is more of an implementation report. So if you're interested in writing down the software, or yeah, like more on the specifications, then read this. If you are, for most network engineers who might find it more useful looking at operational experiences using BGP, then have a look at RFC 4277. So moving forward and discussing more of the characteristics associated with BGP, okay, let's look next at the features. So what are the features of BGP? It's a path vector protocol. Okay, we've mentioned that a little bit earlier on. It's in RFC 1322. So you can read that as well. Generally, there are three common classes of routing protocols. You have distance vector, link state routing, and path vector protocol. OSPF and ISIS can be considered as link state routing. So BGP is a different sort. It is a path vector protocol. So it's a bit like distance vector protocol, but rather than using, say, the number of hops as a metric, we are going to use AS path. Okay, and we'll have understanding of AS path as we go on. Another feature of BGP is it sends incremental updates, so that's a good thing. BGP uses an incremental update strategy so that it can conserve bandwidth and processing power. That is, of course, after the initial exchange of complete routing information. So you have a pair of BGP routers, they exchange these information. Every so often, if there are changes to this, there will be incremental updates going on. Okay? Such an incremental update design requires a reliable transport between your pair of BGP speakers in order to function correctly. Now, have a look at the RFC to have more understanding of how it works in that sense. Now, there are many options for, okay, a lot of people are coming into this session. Okay. There are many options for policy enforcement. Okay, this is because like BGP, you use it normally at the border. One of the main features of BGP is its ability to control incoming and outgoing information. It is implemented in your border routers. I've mentioned about BGP speakers. You'll have at least one BGP speaker sitting at the border of your network. Okay, we call it border routers. They stand between our network and our neighboring network. So this is where we create policies. This is where we control ingress and egress traffic. It can define the types of traffic and from which networks, which IP prefixes will be allowed to enter our network. So you can pretty much have your own policy, enforce these policies based on your organization's business requirements. Next is it uses classless CIDR. It uses classless inter-domain routing. So what is CIDR? Well, basically most of the newer routing protocols uses this. Okay, we will mention about this more as we go on. We'll look at how we can summarize our prefixes, summarize our blocks before announcing them. So BGP4 is the standard that implements CIDR. It is widely used in today's internet backbone. As I've said, it kind of like very important in the in routing or connections between inter-networks. And the current BGP version is MPBGP. If you look at RFC 2858, it defines multi-protocol extensions for BGP4. This allowed BGP4 to carry routing information for multiple networks, different network layer protocols such as IPv6, IPX, etc. So if you are familiar with Cisco terminologies configurations, then you'll see like address family in there. So you can identify either IPv4 address family or the IPv6 address family and configure them separately. Okay, so just like a run through of the most common features of BGP. Now, I've mentioned about path vector protocol, but let's try to understand that in a bit more detail. So what is path vector routing protocol? We'll not go to the details of this, but we want to understand that in order to have a big overview of how BGP works. Path vector routing, it's an inter-domain routing protocol, okay, as compared with link state routing and distance vector, which we have mentioned a little bit earlier on. Both are intra-domain routing protocols. Now, path vector routing protocol is inter-domain. It works between autonomous systems. Now, the important thing to note here is that with path vector, it relies on AS path. It creates a route, sort of like a direction of autonomous systems that your data or your packet traverses from the source going into its destination network. Now, the path vector routing algorithm is somewhat similar to distance vector, as I've said. A border router advertises the destinations or network prefixes that it can reach to its neighboring routers. Okay, so I know how to get to this IP block. This is the path going there, so I will announce that to my neighbors. However, instead of advertising networks in terms of a destination and the distance going into the destination, networks are advertised as destination addresses and path descriptions on how to reach them. So that's what we mean by AS path. BGP keeps a list of every AS that the path has to go through or pass through before it reaches that router. Now, the standard specification of path vector protocol is defined in RFC 1322 if you want to read more about it. So this is an example that I want you to look at. So here we have 1, 2, 3, 4, 6 different networks. They're defined by different AS numbers, right? So autonomous systems are networks by themselves who are defined by two things. One is that it should have its own routing policy, and usually it is run by a single administrator. So you have, yeah, like you may have 2, 3, or 1,000 routers in there, but they may belong to the same autonomous system. So each AS there, so you can see here it has two border routers, and that's how they speak with other networks. So if I want to get my data from AS6461, which is right at the bottom left here, all the way up to AS11268, which is on the upper right side, how do I get there, right? How can I send my traffic there? Thing is, this is where announcements and acceptance would come in. You announce your prefixes, it will be accepted, and then once I get that, I will announce it forward to my neighbors until it reaches the other side. So routing, or sorry, announcing is more of like going this way until AS6461 now have a route entry going into AS11268, and by that, if it is on the routing table, it has the AS path. I know that to get to AS11268, I have to pass through, say, AS7018, AS6337 before I get to my destination. Okay, so that's what we mean by path vector. It lists down all the AS numbers or the networks that I have to pass through before I get to this network. All right, now some more definitions here for us to understand. With BGP, as I've said, it's between networks. And usually there are two ways in which we communicate or connect between networks. And it is dependent on the agreement that we have with them. Now, let's look at these terminologies that we associate with BGP. It defines the arrangement between operators that carry traffic and routing information across networks. One is transit, and the other one is peering. What's the difference between them? You see in a lot of cases it is used in the same way or interchangeably, but there are differences between them. Transit is when you carry traffic through a network, but it usually comes for a fee. You pay someone, okay, maybe a tier 2, tier 1 ISP, so that they will carry your traffic, so that your traffic will pass through them. Transit providers provide internet access from one network operator to another operator. This would come at a cost. Now, small providers get their transit from larger internet providers. Okay, these larger internet providers get them from larger upstream or higher tier providers. Okay, so that is what we mean by transit. You pay someone so that your traffic will pass through. The other one is peering, which is very similar to transit. It's also about exchanging data in some ways, but it's more about exchanging routing information between them. When routers are peering with each other, okay, or these networks are what we call as peers, it means that they are exchanging routing information. It is done at no fee, okay, or sometimes we refer to it as a settlement-free peering. So we peer because we're gaining something from it. Our network is gaining something from it, right? Even if two ISPs, let's say for example, are competing, they can still peer with each other. It's still called a settlement-free peering. And why would they want to do that? If it's more costly for your traffic to pass through, let's say, upstream, just to get to, or maybe it may take longer, just to get to, say, another host that is using ISP, a competitor ISP. Let's say, for example, you have two ISPs, ISP A and ISP B. With ISPA, you have a customer, and he's sending data going to another customer, which is in ISPB. So how soon will my data get to ISPB's customer? Okay, how many hops will it take? If we are not peering with each other, then I have to go through some ways, go to my ISP, maybe even get out of the country before it comes back to ISPB and reach my customer, right? So there are reasons, or there are advantages why you would peer with um, um, even with a competing ISP. So that's a difference mainly between transit and peering. And this last one here is default. Default is where you send the traffic when you don't specify an explicit match in the routing table. You may have default routes. Typically, your provider, your upstream provider, is your default, right? Or if you have more than one, if you have two or three ISPs, you will set one to be the default route of all your commodity traffic. Okay, so it's more like it points to the default link to have access to the rest of the internet if it's not specified. So if you don't have any specifics in your routing table, then default is where it gets to the rest of the internet. Okay, so those three things. Now another one is default free zone, or DFZ. Default free zone is made up of internet routers which have explicit routing information about the rest of the internet. So anyone can do this as long as you have information of all the routes going to every one or every network on the internet, then you can be considered as a default free zone. Most tier 1, tier 2 ISPs are, yeah, usually we tend to believe that if you're tier 2, tier 1 ISPs, you're default free zones. Yes, in most cases you are, but you don't have to be that to become DFZ. But a default free zone requires a router that will carry the full BGP routes, a full BGP table. So how many have we got now? Around 500,000 prefixes are announced on the routing table. Okay, it's not related exactly to where you are in the hierarchy. It's not exactly about like if you're tier 1, you're up default free zone. It's not like that. You are tier 1 if you are not paying anyone for your or anybody else for your internet. While being in a default free zone, well, it may not be good or appropriate for everyone, because it takes a lot of overhead, takes a lot of CPU and memory. So you need a very powerful router to be able to do this. Okay, so it's up to you if you want that. In most cases, what we do is we still rely on one default. We have some set of routes in our routing table, but all of the rest we just forward to our default. All right, is that clear with everybody? Any questions so far? Okay, if you do have questions, just please write them down at any point. I'm seeing the chat every time, so I can quickly try and answer your questions. Let's try and make this as interactive as possible. Here I have an example of peering and transit. So we've already defined peering and transit. We know that with transit, okay, our traffic goes through another network and we pay them for it. So let's look at this one. When are you peering and when are you using transit? You have provider A, B, C, and D. Provider A and B are peering with each other because they are connected to an IXP, an Internet Exchange Point. Okay, so everyone that's connected to the IXP are peering with each other. Now, if they want to get to provider C, which is on the right side here, provider C and provider D are both connected as well to an IXP. So they're also peering with each other. So A and B are peering, C and D are peering. But if I have to send data from A, say going all the way to C, I need to go via provider D. So in that sense, the traffic will have to pass through provider D here. So that is what we call as transit. So A and B are peering, C and D are peering, but A or B going to C, okay, or C going backwards to A and B will have to get transit via provider D. Okay, so that's a very simplified example, and hopefully you would want to do a lot of, let's say, peering, because um, that really helps out. That helps out, say, with the latency, with even with the costs of sending traffic across. All right, next one here is we have, say, this is the definition of an autonomous system. I've mentioned this already earlier on. As I've said, an autonomous system is a group of routers, networks, and they are mostly defined under a single ownership, trust, or administrative control. Okay, and you have to understand autonomous system because we use it a lot with BGP. An AS is considered as the cornerstone of BGP. That's how we identify networks. If you're going to create policies, if you're going to define BGP for our networks, we have to identify the number, the unique number that is associated with an autonomous system. Okay? Each autonomous system has this unique number. We call it as an ASN. It's either 2 byte or 4 byte. It's again, since it's associated with the ASN, with the AS. Now they are obviously allocated. It's like IP. It's a number resource. They are allocated by IANA to the RIRs. So if you need to get an AS number, a public AS number, you have to get them from your either upstreams or from a regional internet registry. So as I've said, an AS, an autonomous system, and an ASN as well, you have to understand them because it's a cornerstone of BGP. If you look at RFC 1930, it says there that definition basically of an AS. Now, if you need an AS number, you can come to APNIC. You can get a 32-bit AS number. You can also get them from your upstream providers, but this is usually a non-portable ASN. Is that clear enough? Now, I want to just go through that quickly because we have a separate session that discusses about autonomous system number and autonomous system in general. So you have more questions on that, you can either ask that here or you can also like attend that session. Now, I want to go to this part. Let's discuss about the operations of BGP. Now, going through some definitions earlier and understanding path vector routing protocol, you should already have a good understanding of how BGP works. Okay, BGP's operation relies a lot on learning or receiving routes, and also in announcing, okay, or originating routes. It involves a series of announcing and accepting. That's how they exchange routing information among peers. And these exchanges happen based on the policies on these different speakers. Okay, so in BGP, what you do is you learn different paths. Okay, it learns multiple paths to different networks from other BGP speaking neighbors. Okay, so let's say for example, I am a router, okay, from network A. I am directly connected to another router in network B. So both of us are BGP speakers. I have connections to other networks either via an internet exchange point, direct peering, or maybe I have customers that are connected to me, and then I'm going to announce their own prefixes. So I have those learned routes that I can now propagate forward and send to my other networks, in this case, to the BGP speaker of network B. In the same way, network B will have connections to the rest of the internet, perhaps, maybe an IXP, maybe another direct peering and all that, and then he can announce those prefixes to me. Now, which ones I would accept and which ones I will announce will be based on my own policy. Now, from all those possible paths, BGP will pick the best one. Okay, so as I said, you learn multiple routes. There are many ways to get to a destination. Maybe it goes via five five networks before it reaches there. Maybe it goes just two hops to go there, but it's on a slower link and all that. So there are many considerations. There are many different metrics. Now, so it will pick the best path. And with BGP, it's about AS path, right? So this routing information will be stored in a table. You have two types of tables. The RIB, which is here, the routing information base, or generally this is what we refer to as the routing table. It is a table of all learned routes. Now, whenever the router learns a new route, it is added onto the RIB. The RIB is now used to build the forwarding table or the forwarding information base, or FIB. Okay, so two basic routing tables there. The routing table itself, or RIB, and the forwarding table, or the FIB. In the routing table, you have all the learned routes. In the FIB, you have the best routes. So you pick the best route amongst the list that is in your routing table. The way BGP picks the best path is influenced also by its own policies. Okay, so going back to the features earlier on, you know how BGP is a powerful tool to implement your organization's policies. So that's the basic operation. Let's have the diagram here. We have AS 100, 101, and 102. Okay, so you notice that there are interconnections. There are BGP speakers there. A, B, C, D, and E are all BGP speakers. You also still have other routers, say within AS 100, but notice at the border you have two routers, and these are the BGP speakers. This one is peering red. It has direct connections, you can see, to router C in AS101. B here is connected to, has direct connections to D, which is also in AS101, and E in AS102. So through this, okay, you see that diagram. That's how how they will exchange information, because they have direct connections to them. So creating a BGP internetwork begins with designing your network. During that design, you assign one router to become the speaker. So in this case, A, B are BGP speakers for AS100, right? From that, so they're now BGP speakers. Now, one of the characteristics of BGP is it should be flexible. So the protocol can connect together any internetwork of autonomous systems using any arbitrary topology. It's actually very independent of that. So their only concern is, like, they have direct connections to another router, and that router also speaks BGP. Okay, that's the only requirement. Each AS should have at least one router that is able to run BGP, and that this router connect to at least one other network's BGP router. Okay, now they have to be physically connected, as you can see here. Okay, there's a physical connection between A and B and C. A and C and B and D. Okay, so that's very important, specifically with eBGP. Now, these other routers are what we call as neighbors. The direct connection between them allows them to exchange routing information about the autonomous systems which they are a part of. Since they are neighbors, they are BGP speakers, they are now peering with each other, okay? And this is done via TCP port 179. So that's where BGP runs. BGP runs on TCP port 179. And yeah, peering is done on point-to-point links between this shared router or shared media, just to his. Any questions on that? So internal and external BGP, let's look at that later on. Now some more terminologies. You have heard me talk about them a lot all throughout. Neighbors. So all BGP speakers that have direct connections are called neighbors. Any two router that have TCP connections, they are exchanging routing information, they are BGP speakers, they are networks. They are peering with each other. Another important ones are, say, with BGP specifically, we have two parts. We have iBGP, which is BGP neighbor relationships between or within the same network, within the same AS, and eBGP. With eBGP, these are the typical ones that we have described so far. Okay, the interconnections between two external or two autonomous networks. And with eBGP, they must be directly connected. So we'll look more into iBGP and eBGP as we go on. I think that's towards yeah, a few more slides before we get there. Now, another important thing to understand with BGP is attributes. So, um, routes that are learned via BGP, they have associated properties, right? They give you extra information. They give you the IP prefix. They give you information on how to get there via the AS path. They give you a few others, like where did this come from? Where's the original? Where is the origin? What is the next hop if I have an entry that matches this? Where do I go next? So these are what we call as properties of your BGP route, or more specifically, we call it as a BGP attribute. So each route prefix have an associated BGP attribute. Okay. Again, this information is about the route, where it came from, how you can reach it. There are two types, well-known and mandatory. So well-known attributes are supported by every BGP implementation. Some well-known attributes are mandatory, meaning that it must be included in every route entry. So if you do, let's say, show IP route and commands like that, you will see your routing table, the prefix is there, and the associated attributes with that. Some of those attributes are mandatory, which should be in every announcements that you receive, say origin, AS path, next hop, local prefs. Those are well-known mandatory attributes. And we also have well-known discretionary attributes, which is not, well, every BGP speaker should be able to recognize them, but they don't have to be present with every route entry, okay? But obviously, if a router receives a route announcement that contains those specifications or attributes, they should be able to recognize them and pass it on forward. Another one is optional attribute. So optional attributes are not necessarily supported by all BGP implementations, so that's why it's optional. There are two types here. They're either transitive or intransitive, or sometimes we call it as non-transitive. It's indicated by a special attribute flag somewhere in the entry. Now, a route is transitive, okay? If a route attribute is transitive optional, then it should be passed along intact to other BGP speakers or the routes, even if this particular router does not understand this option. Okay, if it's not recognized by a router, if it's transitive, it will be passed on forward. If it's non-transitive, on the other hand, it will be dropped from the route information, okay, and the rest will be sent forward. So those are the differences. As I've said, there are many different BGP attributes. You've seen some examples there. You have examples for each, and they can be used to influence how your traffic will be sent or how your traffic will pass. These attributes, if you know how to manipulate them, can be very useful with traffic engineering as well. Okay, so but I won't go through the details of that. As I've said, have a look at the next in this series, which is about BGP attributes, if you are interested to learn more about it. Okay, now we've discussed a little bit about eBGP and iBGP, right? In the previous slide, we have some definitions on there. But when do we use one or the other? What is the difference between them? Okay, BGP is the specification as a whole. iBGP is the part that deals with or all internal routes. eBGP is the one that deals with all the exchange of prefixes between routers or BGP speakers of different autonomous systems or different networks. Okay, so that's the difference between them. iBGP is internal, eBGP is obviously external. But why do we have two different ones? Notice here we have 4 buckets, AS1 to AS4. Any exchange of information between autonomous systems, this one, AS1 to AS2, AS2 to AS3, AS3 to AS4, are all using eBGP. Okay? And then within each AS, you notice that within each bucket, you have iBGP. Okay? And also, you also have there IGP, or say your interior gateway protocols. Like if you are maybe using OSPF or ISIS, that's your IGP. It still runs there. Okay, you don't choose between your IGP or iBGP. They always run in parallel. So why do we have these two? Now, iBGP refers to BGP neighbor relationships within the same AS, right? And it is used to carry information, okay, or internet prefixes across the ISP backbone, okay, and the ISP's customer prefixes only. It is not to be used outside of an AS. So many people have like not sure whether which one to use where, right? Now with eBGP, when BGP neighbor relationships are formed between two peers that belong to different ASs, that's called eBGP. So we've seen this example. Neighbors must have direct connectivity with each of them. And that's how they can exchange prefixes and implement their routing policy. So within this model, we use, I'm using my mouse. We use iBGP because if we have routes that are learned via eBGP from others, from other networks, then it can be passed on to the other routers within our network. So BGP, or more specifically eBGP, doesn't exactly know what happens within an AS. Okay, it has its own internal topology. It uses its own choice of routing protocols. You have your IGP there. Okay, BGP only takes the information conveyed from other networks and shares it within the network. That's where you use your iBGP. Now, if for eBGP you need to be directly connected, okay, one main difference between iBGP and eBGP is that for iBGP you don't have to be directly connected. You can have 5, 10, or 20 routers in there, or maybe even more. They don't have to have direct connections to each of the router. Okay, in eBGP you obviously should have direct connections, right? In iBGP you don't. That's because you already have your underlying IGP that takes care of that part. Okay, it can still forward the packets, forward the information to all the other routers via IGP. But with every iBGP speaker, okay, when you specify or you do your configurations, each of these iBGP speaker must be able to specify all the other iBGP routers in the network. It has to be fully meshed. The reason is purely down to iBGP rules. If you remember, well, if you look at the specifications, it's been there for a while. And in the early days, we don't exactly have, say, routers that are as powerful as what we have now. So within the early days, early developers were afraid that routers will receive, say, lots of updates that might overpower the processor. So they kind of simplified it. Um, so it can only, okay, forward um, information, okay, um, in this way, so that it's this topology is simple. It can scale. Okay, so that's the main difference between iBGP and eBGP in a sense. So notice, just remember this bucket when you kind of like thinking what's iBGP and eBGP. iBGP is within the network. Okay, you forward um, prefixes that are learned from outside, either customer or from the internet, to all the routers within the network if it's iBGP. Okay, so this is more details, more information. You will have a copy of the slides later, so I'll let you go through them. I've already discussed them. Now, this is one example of iBGP. You have A, B, C, and D here. Okay, notice again, if you're doing iBGP, you don't have to be directly connected, but they are peering with every other iBGP speaker within this AS100. Um, Typically, we do this with the loopback interface. Okay, peering is done between loopback interfaces. Why? Because loopback interfaces are virtual interfaces. Okay, so instead of point-to-point links, we use them. Obviously, we can run it using the point-to-point links, but if you look at this diagram here, what happens when one interface goes down? Okay, the iBGP session between router B and router C, for example. I might have this other example. Yep, let's look at this example. So router A, B, and C are peering. Okay, they have iBGP sessions. So this is done in the loopback interface. If it's done in the point-to-point links, think of what will happen if one of the link is down. Okay, the iBGP session between router B and C, obviously, okay, will also go down, right? So router C prefixes will take prefixes learned here and pass it on to A. Router B will take prefixes learned and pass it on to A as well. So A kind of like can see everything, but router A will not pass anything learned from B to C going forward. That means router B and C cannot talk to each other in this case because the link between them is down. So that's what happens if you're using the point-to-point link. So a common practice um, for this setup is to run iBGP on loopback or logical interfaces, which are always up. There is a command in, say, if you're configuring in Cisco routers, that's neighbor update source. This allows you to use IP address of a specified interface as your source IP address for all BGP updates to that neighbor. Okay, now that's peering with loopback interfaces. Now another one is, now how do you now create your forwarding table? So we said that you learn your routes from all the BGP speakers and from their neighbors' neighbors, you get all that possible paths going to a destination. So from here, how do you now create? Okay, how do you select the best one and give it to the FIB or the forwarding table? So it typically works like this. It's kind of a simplified version, of course. Now you have here a BGP in process. Okay, this is the one that I'm talking about. You have a BGP in process, and from here, the BGP speaking router receives the path information from its peers. BGP does path selection process. Okay, so I'll show you the list later on, like how it selects the best path and what to look for. So that's what we call the path selection process. Then based on that, it places it in the BGP table and flags it as the best path. So that's here, that's your process, and then it is added to your BGP table. Now going out, which ones are announced as best path going into the peers? So said the best path is still in the BGP routing table or the forwarding table. Then this routing table is passed on to the BGP out process. This BGP table goes through either the routing table and the forwarding table. The routing table contains all the paths, all the possible paths. The forwarding table only contains the best path. So if the path becomes unavailable, it can get the check the routes again and find the best path from the routing table. Okay, so that's a big picture looking at how this process is done, how prefixes are that are coming in are processed before it goes out and announced further to the neighbors. Next one is, well, this is eBGP and how you interconnect with all the BGP speakers. We've already discussed this. We said that there has to be direct connections, okay, direct connections between all your BGP speakers. Now, another thing that's important to understand here is that this, you should never run an IGP between eBGP peers, okay? So here you have AS100 and AS101. They are two different or separate networks. Now, typically when we're doing a design, we include our customer as part of our IGP, which should not be the case. Well, depending on your setup, of course, or in your design, but generally it should be a different network because your customers and yourself and maybe your upstream or all the other networks that you're peering with will have your own routing policies, and you define those routing policies in your BGP, right? So you don't run IGP between this because it should be BGP where you can set up your own policies. You can allow which ones to go are allowed in and out of your network. Any questions on that? So that's the main things that you have to understand. Now, what actually happens after you've configured the neighbor in your BGP router? Okay, so from that point on forward, of course, routers will exchange BGP messages, and then they will help maintain the states between them. So upon adding the BGP neighbor, both of the routers will establish a TCP connection. They will send an open message. Okay, when this is accepted, both of them will have, let's say, what we call as a keep alive message to check once in a while whether the networks or the neighbors are still peering with them, are still up. This confirms the initial open message sent by both of them. After both parties have sent that keep alive message, they will now establish a BGP neighbor relationship and then can therefore exchange routing information between them. Okay, so they're exchanging a few information. I don't have that in any of these because obviously for here we are very limited. We only have 1 hour to discuss all of this, but that's what happens. They have to exchange a few messages there in order to establish neighbor relationships between them. There are different message types. Check RFC 4271. There's open message, keep alive message, update message, notification messages that can be used for different purposes, of course, when you're exchanging information with the neighbors. So I won't go through those details, but that's a very important part before you actually exchange routing information between the routes. All right, so have a look at RFC 4271 for more details about that. Now, this is the final few slides of this session. Here we have some example of how to configure BGP. We have two examples here. One is, I think, for eBGP and the other one is for iBGP. Okay, so if you're going to configure this with other hardware, maybe you're using another L3 device, it kind of very similar, but here I'm using Cisco router. So how do we configure BGP? Of course, you must know your own AS number. Okay, you must also know your neighbor's AS number. Okay, the network that you're directly connected with, that you're peering with, you must know their AS number. Okay, also I think even their IP address. You also must know what policies you have, so you have an idea of which policies to put in place. We will use the command. Here we have router BGP. This is the command we use, and then followed by the AS number. So this is your AS number. So router BGP 100. I think this is for AS 100. For AS numbers that are greater than 65535, you have two options to do this. Either you use AS plain or AS dot. I would suggest to just use AS plain. That's how we normally do it in this side of the world. But you have the option to also use AS dot, which is kind of this way. Okay. Now, if you don't know the difference between AS plain and AS dot, again, please check the other session on autonomous system numbers. Now, from that, okay, you can specify the BGP and notation, blah, blah, but that's not very important. Here, we have the exact example for router A in AS100. Okay, so this is the definitions, router BGP 100, and then you specify the network and the mask. This is the prefix that you are going to announce, and then you specify who will be your neighbor. In this case, that's 102.102.10.1, which I think is, yeah, router C. Okay, and then for router A, my IP address is 102.102.10.2. Now I specify 3 lines, neighbor, my neighbor's IP address, remote AS 101. So this here, we are doing eBGP because this one is our AS number, this one is our neighbor's AS number. Okay, then you specify your filters. You have inbound filters for this neighbor relationship. You also have outbound filters, again depending on your own organization's policy. So that's one. Now, how does it look like from router C? Router C is in AS101. So very similar, right? We have here, I identified my interface settings. I have router BGP 101, which is my AS number, router C's AS number, and then the remote AS will now be AS100. So you can see that from here. I also specify my own filters, okay? This is my own filters, not dependent on my neighbors. So that's pretty much how you configure eBGP. Okay. Now, is there any special thing to do when you're doing iBGP? If you notice, this one is an example. Okay, sorry, not that one. This one here. This is iBGP configurations. And the structure, the commands and everything are all the same, right? But the only way that we can distinguish that this is iBGP is that we're now using the same AS. Sorry, the same ASN. Router BGP 100 and here router same AS number for our remote AS. So this is iBGP implementation. Okay? But same thing, you have router BGP and then followed by your network prefix and then followed by the list of your neighbors. You can have one, you can have two, you can have many neighbors. But here you have your direct connections from ANC only, right? So you have one neighbor in this case. But in iBGP here, we've done two. Maybe you have more. Again, for each of the routers in your local network, okay, that is participating in iBGP, we're doing full mesh. So you have to specify that for each of the neighbor routers. Okay, in this case, I think we only have three. Yeah, 3 routers, router A. I don't have the diagram in here, but yeah, 2 more routers in the same network. Okay, so that's iBGP. So it's for router B. Now, how do you announce your prefix? There are a few ways to do this, but the one that I typically use is the network command. So router BGP 100, and then you've seen that in the previous examples, you have network and then the mask. And then followed by the IP route. This is your pull-up route. IP route for that prefix, and the interface that is going to use that prefix. All right? So a matching route must exist in the routing table before the network is going to be announced on the rest of the peers. All right, and another one here. This is an aggregated version, I think, for the entire 102.10/16. You can announce an aggregated or summarized version. This is very much encouraged to do. If you have a lot of prefixes, say your customer prefixes, you can combine them all together and announce it, if possible, as a single prefix going into the internet routing table. Okay? Is there anything else? This is an example of the show IP BGP summary, which is a summary of all the neighbors and the routes that are advertised by each of those neighbors. So you notice that here I have peering with 3 other routers in this case, and each of the router is advertising 2 prefixes coming into me. Okay, this is a summarize. If you do remove the sum part at the end, it will give you all of those routes in more detail. Okay, so if you're trying to troubleshoot your, say, your configurations, if you're actually peering with your neighbors, this is a good way to look at it. Okay, and you can see how many prefixes you have got, or whether you have actually established any form of peering relationship with them or not. Okay, so as I've said from the previous slide, you have there the summary. Here you have a list of all the prefixes. These are the network prefixes that are announced, and some attributes. What the attributes you have here? Next hop. Next hop shows you, let's say I have a prefix and it matches with this route entry. Where do I send it next? Yeah, so that's what the next hop value is for. So I send it to 10.0.15.241 interface of my neighbor router. Okay, we also have few here metrics, local preference, weight, and path. Here we have I, because this is, you can check the status codes, this is internal. If you're doing eBGP, then you should see an actual AS path there. I don't have an example here, unfortunately, but you should see there a list of the AS numbers, and then at the end you'll have an I, which means that it's already like you've reached the destination, and everything from there will be internal. All right, so that's an overview of BGP. It's a huge topic, and I think from here on you will want to learn more about it. Learn about the BGP attributes, learn how to apply policies into your BGP configuration, and then learn how to later on perhaps influence how your traffic flows based on your policies and using the different BGP attributes. Okay, so that's the end of this session. Are there any questions from the class? Okay, nothing. This is a pretty quiet class, I would say. But if you do have questions, please write them down. If you want a copy of the slides, it will be available. I'll post the link very shortly. Just looking for the link at the moment. Now, as I've said, we have a survey, and I encourage you to please do this. I'm sure you can click on that link, but just in case you can't, this is also the, no, that's not the link. This is the link to the survey. Oopsie. Should be EL2. This is the link to the survey and the link to the FTP. I'm also going to write them down here. So this is the FTP link. You can download the PDF copy of all the 3 presentations for the day from that FTP page. All right, so is there any other comments, questions from the class? If none, if you can't think of anything at the moment and you're viewing later on and you find something that is not clear, you can always check with us. Do send us an email. We would like to be in contact with you. Send us an email to training@apnic.net for any of your queries. All right, so with that, I'd like to thank you for your time and for your attention, and I hope to see you in the next e-learning session. Bye-bye.